in the early 1960s. At the dawn of the new age of space, a new breed of powerful launch vehicles was conceived. First, from a cluster of tanks from proven smaller rockets, and later to land a man on the surface of the moon.
Liftoff. We have a liftoff. 32 minutes past the hour.
That's one small step for man.
Their creation would test the limits of what man can accomplish with machine and bring forth new ideas on systems management, force the creation of new materials and techniques. But most of all, they harnessed power on a scale never before imagined and launched it into the heaven. It is the spring of 1958, and the Cold War is at its coldest. A group of engineers brought to the United States at the end of World War II and led by Wernher von Braun are working to give the Army the capability to lift massive weights into space. The Army is looking for a new weapon system, but the engineers have other dreams.
Of course, von Braun always wanted to go to the moon. His main goal was really not the development of a military weapon.
Konrad Dannenberg is a rocket propulsion engineer with the original group of rocket scientists brought from Germany to the United States after World War II.
The Saturn was really started by the Army. So it was not initially a NASA project. In fact, NASA, when the Saturn program was started, did not even exist.
And the Army was in a hurry. Interested in a new booster with a thrust of 1.5 million pounds and interested in it quickly, von Braun's team fell back on proven materials and hardware to get the job done.
Our organization received an assignment to put 8 Jupiter rocket engines together in a cluster and try to focus them into working simultaneously.
The team had a great deal of experience with its own Jupiter engines, and so proposed clustering 8 of the engines together to create the Super Jupiter, or the Juno 5. Later, this would become Saturn I. By using off-the-shelf hardware, a big booster could be developed quickly.
It wasn't a great leap other than the fact that you clustered these engines. You had to worry a little bit about the interaction of the engines. The tankage was essentially the same, had already been built and developed. We repackaged the engine, and Rocketdyne had some problems in the repackaging. They put the turbo pumps, hung them on the thrust chamber as opposed to putting them up in a separate structure.
Bob Lindstrom was a project engineer and program manager for the Saturn I.
The Advanced Research Project Agency, part of the Department of Defense, started a big booster program. And they looked at a number of vehicles, and they finally settled on a booster that ABMA could put together, which was a cluster of engines from Rocketdyne, which were derived from both the Thor and the Jupiter missiles.
The concept behind the early Saturn I rocket was straightforward. Take tanks and engines from the successful Redstone and Jupiter programs, cluster 8 Redstone tanks around one Jupiter tank, cluster 8 H-1 engines at the base, and create a massive booster much larger than anything seen before.
We succeeded pretty well. After all, we had a reliable engine to begin with, and soon we had a booster of a total of 1.5 million pounds of thrust. It is this booster that powered our 10 successful Saturn I rockets and also the 3 upgraded Saturn I's that followed.
The big issue was, managing the propellant flow in between the tanks, balancing that out and make sure you didn't have any big problems or any interaction with the engines. And we had very little interaction.
Before Kennedy's announcement on the lunar program, the center was responsible for building the first stage of a Saturn I, not to fly, but only to prove that it could be done and that you could static fire it.
Jay Foster was a project manager for Saturn I.
Well, clustering them together in this thing, and In some ways it's exciting, and it was exciting, but at the same time, you know, individual jobs are in some ways fairly routine.
While the original program was only to develop a demonstration stage that could be static tested, it was quickly expanded to a 4-vehicle flight program.
Before we went to NASA, ARPA asked for a program that would turn into a flight program. And so ABMA, Dromadaris proposed a 4-vehicle program. I forget the amount of money he did, but I was there when he presented to him by telecon. In those days, everyone used a telecon. It was very difficult because it was classified, you know, and they'd answer and we'd answer them. I didn't do much answering, but listen to Madaris. But we proposed 4 flights with some unknown payload on the 4th vehicle.
But the making of the Saturn was a big increase in scale. A test stand originally intended for the Jupiter's 165,000 pounds of thrust had to be rebuilt to take 1.5 million, and all in a span of 18 months.
We had to build some big scaffolding to go around this Saturn I to put all of these different tanks together. And this thing was about a 4-story, in effect, a 4-story building, so there was a lot of discussion about whether we should have an elevator or whether it was stairs. And Hans Maus decided on an elevator, but he had also established a planning board. Well, Hans Maus went off on a vacation for 2 or 3 weeks, and shortly after he left, Werner Kurs called a meeting of the manufacturing planning board and convinced us all we really didn't need an elevator. So Hans Maus came back 3 weeks later or so and found out we didn't have an elevator, and anybody at the ceiling. We ended up with an elevator.
But there were problems. With the 8 tanks with alternating fuel and liquid oxygen, and a center tank full of liquid oxygen, sloshing propellants could play havoc with the performance of the vehicle.
The engineers came up with some fairly interesting, they used what they call the beer cans. They weren't really beer cans, they were approximately the size of beer cans. They were made out of aluminum, and these things would float on top of the liquid oxygen, and when the vehicle would shake and would roll, they would damp out these vibrations.
A more permanent solution of baffles were developed to reduce sloshing, and on many flights, television systems were employed to monitor the actions of propellants inside the tanks. The systems would transmit real-time images to monitors for recording and study of propellant behavior. But in these early days, money was tight.
We spent all the money for this first Saturn I, but while we're giving this presentation to von Braun about why we needed extra money, and Maus basically said the point, says, Werner, so you know, I'm building this Saturn I together, and I've got the center tank, and I've got 7 of the outer tanks, and I just run out of money. I don't have that 8th tank, and you know, if you don't give me more money, you can't build this vehicle with only 7 tanks, and you know, which was almost like, you know, putting the gun to von Braun's head. You know, he didn't have any choice. But we got a big chunk of whatever reserve monies that von Braun had, because we had to have that 8th tank to go into the first Saturn I vehicle.
In the late 1950s, change was a way of life in the new business of space. Ed Buckby handled public affairs at the Marshall Space Center in Huntsville, Alabama, during the early Saturn years.
Well, in the early days, the Army was not in the exploration of space business. I think von Braun brought that dream with him.
So just as the engines began arriving and the project began to roll, the Army, becoming suspicious of the real role for Saturn in a world of spaceflight, decided to cancel the Saturn program, believing the booster just too big for a military application. In late September 1959, a move began to transfer the von Braun team to the new NASA. And so by early 1960, the team to develop the Saturns for space flight had begun to come together.
Von Braun was a very gracious individual, you know. He very seldom put blame on people for anything. He didn't criticize people, you know, he listened to people. Sometimes, occasionally, he went off by himself and made the decisions, but he was from a standpoint, that was a very democratic type of leader, you know.
He was a very wonderful individual. Everybody loved him. He never gave a direct order in a way. he could always sit down and talk to you. He had this wonderful gift of gab, and in the process of discussing things with you, I mean, he would inevitably get you around to his way of thinking. I mean, occasionally you could get him around to your way of thinking, but normally he was way ahead of you in the smarts department, and he could convince you that what you really wanted to do was what he wanted you to do, but without giving a direct order.
He never built anything. He never developed anything just for today. The Saturn was, a vehicle that he had conceived as not only to take care of our moon flights, but also to build a station, to possibly have a nuclear stage on top and go to Mars. And we never were satisfied with what we were doing today. We were always looking beyond the next mission.
He had the capability of making you want to work for him. He was a leader. I don't know if he was a scientist, but he sure was a leader. I had a German TV station a year ago asked me, did I think of von Braun as a German, a Nazi, or an American? I just don't tell the truth. I never thought about it. So.
And I remember this one letter came from this German guy who was graduating, and he said, I just can't understand. I can't grasp what I should do next. I'm coming out of college. I've got an engineering degree. I've got this job offer from the local utility company, but I'd like your thoughts. And so we wrote a long letter addressed to this gentleman for von Braun's signature. Von Braun looked at the letter, crossed through it, and said, "Dear Hans, come to America. We're going to the moon."
But the moon was still a long way away. Thus far, Saturn hadn't left the ground, and it was time to see if the clustered concept would really work. By the early 1960s, the United States was well into development of a series of large launch vehicles, the Saturns. The early Saturns, born of an Army project and transferred to NASA along with a von Braun team of engineers, was ready to fly. Of a conservative nature, the rocket team practiced an incremental approach to flight testing, developing stage 1 carefully, then adding additional stages as the lower stages were well understood. So the first 4 flights of the Saturn I would be single-stage flights. The payload consisted of a dummy upper stage of the same weight and configuration of a flight stage. A Jupiter nose cone topped off the vehicle, which stood at around 50 meters. Only after the first 4 flights would a live upper stage be added.
I recall, the flights were almost nearly perfect.
In fact, for introductory rocket flights of the time, the Saturn record was extraordinary. The flights were nearly perfect, and very few modifications were made from one vehicle to the next. The first Saturn, SA-1, left the pad on October 27, 1961. The booster climbed to an altitude of 137 kilometers and impacted the Atlantic Ocean 344 kilometers downrange. SA-1 did reveal a surprising amount of propellant sloshing, and beginning with the third flight, anti-slosh baffles would be added to the tanks. SA-2 departed Pad 34 on April 25, 1962, and was the first of 2 experiments called Project Highwater. The inert upper stages of SA-2 and SA-3 carried 30,000 gallons of water. In an experiment to determine what might happen to liquid in a rocket stage exploded at high altitude, the upper stages of the second and third flights were destroyed at 105 kilometers above the Atlantic. The resulting ice cloud extended upward to an altitude of 145 kilometers. SA-3 was launched on November 16, 1962. and in addition to being the second Project Highwater flight, carried 4 solid-fuel retro rockets in order to prepare for the later addition of a second stage. The last of the original test flights, SA-4, left the ground on March 28, 1963, and not only fired experimental retro rockets, but also carried simulated camera pods and simulated ullage rockets on the inert S-4 stage. Ullage rockets are used to seat propellants in a rocket stage prior to ignition, and comes from an old brewer's term. SA-4 was also an important test of the clustered concept. 100 seconds into the flight, one of the 8 H-1 engines was shut down on purpose. As planned, the rocket remained on course by burning the remaining 7 engines longer. As the first Saturns were taking to the skies, events in the country were turning the course toward the moon, and the results were being felt in Saturn. Having boldly given the country a goal to reach the moon in the 1960s, President Kennedy traveled to Huntsville to meet face-to-face with von Braun.
I don't think he was comfortable with the fact that he had set this goal, and he didn't really know if we could carry it out. So he came to see the man that had the rocket that gets to the moon. And it was obvious when he arrived at Redstone Airfield and got off Air Force One, and he and von Braun met, and they climbed in that limousine, the open-top limousine, you could see the chemistry. And they met and they mixed very well. They bonded, I would say, as well as you could expect them to.
I managed to stand next to the president, or not next to the president, but in the group when the president and the vice president and Mr. Webb and von Braun when Gerald Wiesner got in a discussion of the how best to accomplish the Apollo program. You know, I'm sort of standing off, because the thing I remember is they talked for a long time, and Brainerd Holmes, who was the guy running the Apollo program in Washington, was off the side. I remember Mr. Webb motioning to Holmes, couldn't get in the discussion. The thing I remember most was, you know, the president, he didn't say a word. But all of a sudden he'd heard enough, and he just nodded his head, and everybody stopped and they all left, you know. I sort of remember he had very steely gray eyes.
And Kennedy at one time, you know, came right out and said, Dr. von Braun, can we accomplish this mission within the time I've set? And von Braun said, yes, sir, Mr. President, we can do it, and we're going to do it within the time frame you set.
I stand at the airport when the president left, stand next to Dr. Reese, Mr. Reese, who was von Braun's deputy. I think the press plane took off first, I don't recall, but it took off very nicely. If I recall, it was a Pan Am jet, you know, got up in the air quickly. And then the president's plane took off, you know, belching smoke all the way down the runway. I guess they had their afterburners on or something. And Reese said, see, they got their fuel from the lowest bidder.
Unfortunately, the president did not get to see a Saturn V firing. He did see a Saturn I, and nor did he ever see a launch. But he saw the makings, and he was so moved by that test firing that day.
The Saturn I first stage had proven to be a powerful, reliable vehicle, but did not have the ability to reach orbit on its own. Now engineers would add an upper stage to give Saturn the capability to reach orbit. Conventional rockets used hydrocarbon fuels, and the Saturn I first stage was no different, releasing its energy from a combination of RP-1, a form of kerosene, and liquid oxygen. But the new Saturn upper stage would use the higher energy combination of liquid hydrogen and liquid oxygen. Liquid oxygen was cryogenic, cold enough at 297 degrees below zero, but it would convert to a solid if exposed to the temperature of liquid hydrogen at 423 degrees below zero. While more complicated than a conventional RP-1 power plant, hydrogen offered greater specific impulse in rocket engines, or greater power for propellant weight. The new combination of propellant had been under development since the late 1940s and was just being developed for spaceflight in the Centaur program. The Centaur was an upper stage for the Atlas and used 2 of the new RL-10 hydrogen-oxygen engines with 15,000 pounds of thrust. The original plan for the Saturn upper stage was to cluster 4 engines.
I remember we went from the 4-engine S4 to the 6-engine S4. And we were walking around Douglas's plant in Santa Monica with a guy from Los Angeles Ordnance District and told him the decision had been made to go to 6 engines. And he gave him directions right there, you know. He gave him contractual directions.
As finally configured, the S4 stage would cluster 6 RL-10 engines. In the case of the S4, technological leaps were required. In fact, after specifications were set, only 11 bidders were interested in competing for the task. Douglas eventually won the contract.
That engine was started also by ARPA as a part of the Centaur program, you know, by Pratt. And they had a lot of problems with it. And we had a fair number of problems with Douglas building it.
In order to save weight, the stage would use a common bulkhead separating the oxygen and the hydrogen, and developing insulation of the hydrogen tank to prevent heat flow to the adjacent oxygen was a challenge. One important decision was the choice of using internal insulation. Individual tiles were used, foreshadowing the future Space Shuttle thermal protection system. They were numbered for placement and glued within the stage, each in its proper location. The adhesive surface between the insulation and the structure was not exposed to cryogenic temperatures and was protected from external aerodynamic forces. The aluminum construction of the stage, with a very high coefficient of expansion due to temperature, would not be exposed to the extremes of liquid hydrogen. At the time of the S4, large quantities of liquid hydrogen were not readily available, and new plants were created to produce the exotic new fuel.
Oxygen hydrogen was an issue, obviously, you know. Even, you know, how you get it, where you build a plant for it, you know. And eventually they put a hydrogen plant in Saturn right outside of the gates at Kennedy Center.
Issue by issue, the problems were worked. The engines and the stage was tested, and the Saturn was ready to add the S4. Along with the addition of the new stage, the booster was uprated as well, with improved engines that placed the total thrust at just over 1.5 million pounds. To feed the hunger of the extra power, the length of the propellant containers had been increased. Because of the reliability of the H1 engines, the hold down time of the booster was reduced from 3.6 seconds to 3.1 seconds, resulting in more fuel being available for powered flight. And the Saturn team had learned how to better utilize all the fuel that was aboard. SA-1 had used 96.1% of its fuel, and at the time of the final Saturn I flight, that figure had risen to 99.3%. To study stage separation and the performance of the S4, a number of new visual systems were added, including more television coverage and film camera pods.
7, 6, 5, 4, 3, 2, 1. Liftoff plus 2, 3, 4, 5.
The first launch of a Saturn I with a live upper stage was the SA-5 mission, launched on January 29, 1964. It marked a number of firsts for Saturn, including the first to fly guidance and control packages, first Saturn stage separation, and the first Saturn orbital vehicle. It was also the first recovery of motion picture pods on Saturn, yielding some of the most overwhelming images of the project. SA-5 was a textbook launch, further proof that the Saturn I vehicle was powerful, reliable transportation into orbit. Now the Saturns would begin to be put to work, qualifying and testing the Apollo hardware that would take a man to the moon. The Saturn I vehicles were proven and reliable. Incredibly, the Saturns had scored 5 picture-perfect missions, including the first orbital Saturn flight, combining a successful booster in the S1 stage, and now a high-energy upper stage with the S4. The Saturn was to begin a series of flights to test Apollo hardware and examine the space environment to confirm the safety of the Apollo design. SA-6 roared off the pad on May 28, 1964, and was the first to carry a dummy Apollo capsule all the way to orbit. The flight caused some concern when one of the first stage engines, number 8, shut down unexpectedly 117 seconds into flight. Telemetry revealed that the failure was due to stripped gears in the turbo pump, and a modified design had already been incorporated for the next flight. SA-7 left Earth on September 18, 1964, and after the flight, the Saturn vehicles were declared operational. The SA-7 camera pods were not picked up right away, being consumed by Hurricane Gladys. But 7 weeks later, 2 of the capsules washed ashore, with the film undamaged. SA-7's payload was Apollo Boilerplate 15, and the flight was a complete success. The last 3 flights of the Saturn I series were to loft a payload called Pegasus into Earth orbit. Designed to extend panels to determine the rate of micrometeoroid impacts in Earth orbit, the Pegasus satellites confirmed the rates were well within expectations considered for Apollo Saturn design. Most of the S1 first stages were manufactured in-house by Marshall Space Flight Center, with later booster construction being contracted to the Chrysler Corporation. Because of the changeover, SA-9, a Marshall booster, flew before SA-8, the first Chrysler booster. SA-9 would carry the first Pegasus satellite. The Pegasus was attached to the forward end of the S4 stage, and its huge panels were deployed over a 60-second period. SA-9 was launched on February 16, 1965. An onboard television system monitored the deployment. SA-8 carried Pegasus 2 into orbit in the first night launch of a Saturn vehicle. On July 30th, SA-10, the last of the Saturn I vehicles, left Pad 37B carrying the Pegasus 3 satellite. Saturn I, with a perfect success rate, was over. And while closely related, the Saturn 1B would be a new vehicle and accomplish new missions, including launching a manned Apollo spacecraft into orbit for the first time. The Saturn 1B consisted of an improved S1 first stage and a completely new upper stage, the S4B. The first stage of the Saturn 1B was improved over the Saturn I, with redesigned fins, uprated engines taking the thrust from 188,000 pounds each to 200,000 pounds, and new fabrication improvements resulting in the saving of considerable weight. Perhaps most importantly, the Saturn 1B enabled flight testing of hardware that was to be later used on the Saturn V. The Saturn 1B second stage would also be the third stage of the moon rocket, with some minor differences. Although the design would be similar, the S4B was a completely new machine, and the only commonality with the S4 was the use of the hydrogen-oxygen combination. Mounting a single J2 engine, the S4B thrust of 200,000 pounds was significantly more powerful than the 6-engine cluster on the S4. Many of the insulation and fabrication difficulties of a hydrogen-oxygen stage like the S4B had already been worked through by Douglas on the S4 stage. In fact, the S4B did not go to competitive bidding. It was bought directly from Douglas, sole source by the government. The first Saturn 1B flight left Pad 34 on February 26, 1966. The vehicle, SA-201, was a 32-minute suborbital flight. The primary test of the mission was the separation of the spacecraft and a test of the Apollo spacecraft's heat shield. On the Saturn 1B flights, only 2 cameras were flown to document stage separation, and 1 was not recovered. Next up would be AS-203. With AS-202 delayed for additional checkout time needed for its Apollo spacecraft, since AS-203 was primarily designed as a launch vehicle development flight, it carried a nose cone rather than an Apollo spacecraft, and much of the data sought concerned the behavior of the propellants in orbit for extended periods of time. Since the S-4B was required to restart up to several hours after liftoff in order to place the Apollo spacecraft on a lunar trajectory, data was required on the behavior of the stage during parking orbit. AS-203 was launched July 5, 1966, and after an outstanding flight and simulated J2 restart sequence, the S-4B stage was tested to failure in Earth orbit, disintegrating when the common bulkhead failed due to high pressure. AS-202 was launched on August 25, 1966, and was a suborbital flight designed to test the Apollo heat shield. A skipping re-entry gave the Apollo a real workout, clearing the way for manned Apollo flights to begin. The first manned Apollo mission was scheduled for February 21, 1967. The AS-204 vehicle would become Apollo 1. But on January 27, 1967, a fire in the pure oxygen atmosphere of the spacecraft during a ground test handed the program tragedy. Gus Grissom, Ed White, and Roger Chaffee were gone. And it would be nearly a year before the Saturn 1B would rise again, and with it, the first flight of the vehicle destined for the moon. The AS-204 booster would eventually leave the Earth on a successful mission. Apollo 5 left Pad 37 on January 22, 1968. It carried a lunar module in its spacecraft lunar module adapter for an unmanned test of the lander's propulsion systems and structures in Earth orbit. The successful flight of Apollo 5 was a milestone on the way to the moon, a flawless launch vehicle and spacecraft separation, and a positive first flight for the lunar spacecraft. Now, the way was clear for 3 astronauts to climb aboard a Saturn and ride it into space. The AS-205 flight was Apollo 7 and carried Wally Schirra, Don Isley, and Walt Cunningham into Earth orbit for a thorough workout of Apollo systems. Once again, the Saturn performed flawlessly, and the torch was passed to the Saturn V to place men on the moon.
Apollo 11, this is Houston. You are go for GLI, over.
We believe that Mike Collins is now maneuvering the spacecraft.
Loud and clear now, Mike, and we understand that you are docked.
That's right.
Roger, Eagle, done dock.
Roger, how does it look?
Eagle has lead.
Roger. 20 feet, down and a half. Looking forward, just a little bit. Good. Okay. Houston, tranquility base here. The Eagle has landed.
Here, man, from the planet Earth. First step foot upon the moon. July 1969, AD. It came in peace for all mankind.
With the moon landing goal complete and the Saturn 1B man-rated and fully developed, the Saturn 1B vehicle became the United States' most economical transport to Earth orbit. It was in this role that 1B was used to safely launch 3 crews to the Skylab space station. AS-206 was launched on May 25, 1973, and carried the first Skylab crew, designated Skylab 2, for a 28-day stay. Having been launched 9 days earlier on the last Saturn V, Skylab itself was in trouble. During launch, the station's micrometeoroid thermal shield and one of its solar arrays was torn off by the stress of launch. When it reached orbit, temperatures in the station began to soar, rising above the level of habitability. Now, it was up to the first Skylab crew to deploy an umbrella-like sun shield to protect the station and lower the internal temperature. Since the launches came 5 years after the last use of a Saturn 1B, the missions were launched from Launch Complex 39 using Saturn V hardware. The vehicle sat upon a tower called a milk stool to enable it to use a launch facility designed for a much larger rocket. The Skylab 3 crew flew to the station aboard AS-207 and stayed aboard Skylab for 59 days. Skylab 4 broke space duration records by staying aboard Skylab for 84 days. The AS-209 vehicle was also assigned to the Skylab program as a rescue vehicle, but was never used and is now on display at the Kennedy Space Center Visitor Center. Finally, on July 15, 1975, the last launch of the Saturn Apollo program, the Saturn 1B lifted CSM-111 to a successful docking with a Soyuz spacecraft. The Apollo-Soyuz test project marked another successful performance for the Saturn 1B and closed out the incredibly successful record of the vehicle. 15 men rode the Saturn 1B into orbit, and the next Americans into space would not fly until 1981 when space shuttle flights began. From first flight in 1961 to the Apollo-Soyuz test project in 1975, the early Saturns were powerful workhorses in the United States arsenal, leaving behind a 14-year legacy of achievement. Eclipsed by the enormous power and glamour of the Saturn V, the early Saturns are often overlooked for the enormous contribution to American success in space. Through the development and flight testing of the early Saturns, the mission operations and launch crews learned the valuable lessons that brought success on the way to the moon and beyond.